Been off in the set. All right, so we're going to sort of take the ideas of simulation that Dave gave us a moment ago. It's perhaps, this is a sign of bad judgment at the end of a long day, but Tom Schneider was a very generous and self-identified reviewer of our textbook, and in the process of writing the book, I had pointed out that these scenario models are great, but they're really fiddly and hard to do, and you guys like just a complicated thing. And his response was, "Yeah, nature's complicated. Get over it." So yes, they're difficult. There's a lot of things to them, but it's that flexibility that makes them so powerful, actually. And so I think he's rightly a little bit sensitive to the fact that people complain about the fact that nature's a difficult thing to deal with. So what I'm going to spend the day now, we have two more sessions left in the workshop. So for this next one, I'm going to focus on, and you get to hear me the entire time. So, but hopefully not just me, at least for the last one. But the plan is to talk about this notion of simulations, which are model-based simulations and estimation-based simulations that David just talked about, and move on to this notion of agent-based or de novo simulations. And so. This is that one time in your scientific career when making up data is a good thing to do. So, we're going to talk about a smart way to do it. And this is a much bigger sort of project than we can talk about here. It's not really just networks, but we're going to give you the network side of it, that it's there. But the goal is to help you understand sort of the potential of simulation models and what they can be used for, as well as to try to give you a handful of, cautionary signposts to say, you might be tempted to do this, but think twice before you do. So that's where we're going to go today. Okay. So we're going to start with what, why, and types. Then we're going to go through a basic rubric that I've come up with over a while to think about simulation elements. And then we're going to effectively go through a set of case studies. So, and we'll end with a little bit of not so much an R code sort of, like I'm not going to give you a piece, but I'll point out some hints. So. You can make things up. Simulations run the gamut from simple randomizations, right, where you're trying to figure out something's going on, to a really full-blown model. And so fundamentally the goal is to make up data in a way that answers a real question. And the kind of question you want to ask is really dependent on the situation that you're dealing with. And so the reasons that you would do simulations are probably the first biggest one is that it's just lack of data. Like you can't go out and get it. You would like to have a data that exists there. I would love to be able to figure out how disease moves through a population, but actually finding all the data out there that I would need to do that at the micro level that I want is just impossible. It's also often unethical to do it, right? So one way I could figure out how disease moves through a population would be if I could have snuck someone into this room with an infectious disease and seen how long at the end of the day you guys get it in, but IRB won't let me do that, right? So I can't use you as human subjects to seed a disease or something like this. And there's of course a million types of things like this that you couldn't do it. You couldn't pick people up and move their housing and so forth. And so there's a whole series of questions where the data just are either unavailable in practice or unavailable for ethical or theoretical or real reasons of the way the world works that you couldn't possibly do it. I think more interesting in some ways are that we want to figure out simulations to extend theory. And so we want to, the thing you're going to, the story, to give away the ending, the story here is that simulations are what you put in them. And the key is to put in them things that are informative. And most of the time, theories are informative when you have some complicated understanding of the world, lots of feedback loops, lots of processes that are contingent on each other, and it's too complicated to write down a simple equation for or to estimate a model on, but you want to find a way to ask how the process, what it implies. And so oftentimes, I think, we as social theorists have pretty good intuitions, if not formal models, of micro behaviors. We know we have things like we understand jealousy or we understand desire, or sort of things at the individual level, but how those aggregate up and how a reasonable feedback process is going to make the whole system evolve is really unknown. So we need to think very carefully about that. So in particular, I think probably the biggest feature of networks, or of particularly network simulations, is that our processes of forming a network and the agents, what they do on the network, have these built-in feedback loops. So the people I'm friends with, we start acting similar. Our similarity then selects us into other kinds of behaviors, and so that feature creates a feedback loop that's really hard to model from a statistical standpoint, but it's there. So then there's another feature which is obvious that you've seen a lot of this already in this workshop, which is statistical validation. So lots of times we've developed methods or measures, and we want to know that they work the way we think they work. And so oftentimes just doing Monte Carlo simulations are a very easy way to get to that. We do a lot of that as well. And finally, there's a lot of sample and construction issues that we need to think about in terms of networks. Remember, the assumption of network data is that you have the full population, but oftentimes you don't really have the full population. And so for cost reasons or sample response rates or whatever, you might have 80% of the population, you might have 40% of the population. And so if you have a model of what that looks like, you can then simulate up to the population you actually think you have that is effective for what you need to do. All right, so what are the types of simulations you can do? I think that there are a series of, these are dimensions that there's no guiding theory behind these dimensions. These are Moody's ad hoc characteristics of what a simulation exceeds. So take that for what it is. But I think that these are three plausible things that you want to think about, or dimensions of simulations. The first is like, why are you doing it? Is it that you're trying to predict something in the world, or are you trying to illustrate a feature of some kind of an intervention or process or something like this? So if I'm designing a simulation study so that the Social Security Administration doesn't run out of money, right, that's a simulation where I'm really trying to predict like how many people are going to retire, how long they're going to be on benefits, how long they're going to live, what kind of dependents they're going to have, right? So this is a prediction kind of model. And in that kind of model, it really needs to be grounded in data and very clearly validated at each micro step to make sure that where I'm going is a plausible feature. If what I want to know is instead whether or not you're better off vaccinating kids in schools versus kids at home, then maybe that's a kind of an illustrative process where I could set up a toy example and have all of the basic elements of that process right, but I'm not trying to model any particular school. I'm trying to show that there's a difference between lots of small vaccinations versus one mass vaccination, say, just to make an example off as we go. You can have a version that is a grounded theory versus a data-based theory. And so oftentimes what you'll do is you'll take a series of observations from the real world, and this is what Siena is doing in many ways, and it's saying, how do I simulate from one observation to another and take the element in the middle that I don't know and impute what's there to try to figure out the best feature that would get me from A to B. That's a nice grounded data-based simulation. In many types of cases, that's the type of thing we want to do. We want to figure out how much data is there, and we'll take that and move it forward. In other times, we just have a theoretical set of propositions, and we know nothing about the underlying data. And so we really are making things up completely from scratch. So I have a sense, say, that there's, that Martians probably have homophily, but I have no data on Martian homophily, despite what the History Channel shows me. So I'm going to spend my time sort of thinking about how they select certain people and so forth, and it's completely made up, right? But presumably I'm doing it because there's something about the world that I care about, something about theory, say reciprocity or simulation of some sort that I want to deal with. Finally, there's a realism question, and this is a bugger. One of the things that people do once they figure out what they want to simulate in the world, they need to figure out how real they want it to be. And your instinct is going to be to make things real. And I'm going to caution you to be really careful to have only the reality you need to have in the simulation. Because even the simplest of these simulations get really difficult really quickly. And so once you start saying, well, I'm going to model the spread of disease in workshops, and so I'm going to have a bunch of agents come into a room. I'm going to have a certain level of spread of disease that I'm going to put on there. So all the basics that you might put in. Then they say, well, I'm going to figure out where people sit. I'm going to figure out, what color shirts they're wearing. I'm going to figure out, whether they're eating at the coffee at the same time or not. Like, it's 1,000 little details you can put in, and most of those aren't going to be relevant. And the real problem is, once you get to that level of detail, you're going to end up with a mess that you can't interpret. So there's this balance process between interpretability and understanding, and realism that, again, is going to feed into these other features. If you need to predict, you might need more realism than if you're trying to just understand or illustrate, but those features are feedback. There's a feedback in that process as well. So you can think about these dimensions of sort of realism prediction versus theory and data, and there's a whole bunch of examples out there in the world that we've seen. So up in the far corner over there are things where you have realistic data, realistic database models, and I think Sienna simulations are a good example of this. The EpiSim models, the EpiModel simulations, which is a tool that Sam Jensis developed to help you figure out how likely disease is to move on a network. It was built in an HIV context. That's really nicely built to be realist. The CoreSim model, which was developed for Social Security Administration, right? These kinds of models are really detailed and very grounded in data. And their goal is to predict the next year of Social Security, for example, what it needs to keep funded. A lot of the COVID modeling simulations like this, they've been all over the board, right? So I've put it in the middle here because there's a range of them. Some of them that I've done for COVID simulation, myself and Dana and a few others in this room. This work was built like purely on a toy model. It's like, let's assume that masks work, and let's assume that vaccines work, and we'll put a range on that. And then the mixing is almost random, and we can figure out sort of how much adoption affects the likelihood of a big pandemic versus a small pandemic. Whereas when Jimmy Adams was working on the Colorado COVID task force, they were building compartmental models where the compartments might have only a few thousand people in them. So very detailed spatial and demographic compartment models, which was really much more realistic. And so they had different purposes, but that was the goal. On the other, there's some really great demonstration models, and I'll show a couple of these as well, like the Schelling segregation model, which says, let's imagine that we have a very simple idea, that people get to choose who they live next to. And what's the global implication of that simple individual idea? And we're going to ignore history, we're going to ignore actual geography, we're going to boil this thing down to the simplest possible problem of what happens when you aggregate individual choices. And it finds out it's kind of illustrative and interesting. So I want to show that first. Yeah, I'll do that in a second. So for any given simulation, so that's all about framing. So that's the kind of things you should do or think about before you ever put anything into the world. Once you decide what it is you want to get out of your simulation, usually it has these three elements. The first is an environment. There's some setting within which your agents work. In our case, that environment is usually a network, right? But it need not be. Like oftentimes it'll just be an in-by-in grid of spaces where people go. Or there's a famous simulation called Sugarscape where ants are generating resources and consuming it at a certain rate, right? And so in that case, the population is nothing at all of interesting. There's another great simulation that's been done on disaster response in Portland, Oregon, where they've literally mapped every address in the city, and they've asked what happens when a flood happens, and what happens if there's an earthquake, and what highways can people go on. So your environment could be incredibly real, or it can be completely abstract, but it depends. But there is something that your agents have to move around in, and they have to do something in. Then the biggest piece that are probably these next two, which are your agents. The agents are the actors in your model that do something, right? And there can be many types of agents. In most of our cases, these are probably meant to represent people or people in organizations. But the agents are agentic. They do something. They make choices usually, or they engage in some behavior. Sometimes that behavior is as simple as being susceptible to disease and getting sick and then passing it on to someone else. So it might not be a particularly interesting agent. Other times, like they're balancing between lots of different opportunities that they can do, and you have a reason for how they would weigh those features. The reason for how they weigh those features are your rule set. And so the rule set are the set of behaviors that you expect agents to engage in given the conditions they're faced with. And so there's always this mapping between what people should do and the situation they find themselves in. So it might be that when I get sick, when I start feeling a bit of symptoms, I stay home so I don't give my disease to someone else. So that would be a rule, that there's some sensitivity, some self-segregating feature that sick people have that should stop them when they're symptomatic from doing something. And so that would be an example of a rule. Another rule would be if I don't have at least half of my neighbors that are like me, I'm going to move somewhere else, right? So that's the kind of rule. But it's always always. Is that true? I never say always. It's usually. It's usually the case that it's this intersection of a situation they find themselves in and a choice they have to make. And the reason that it's that is because the situation they find themselves is the result of the choices other agents have made in a prior time step. So that's what creates the feedback loop. And so the idea is that the setting creates the conditions for which the next agent has to make a choice, and it's that feedback process which is of interest. So a really fun example is the Schelling segregation model. And so Schelling, this model, I should have put the date up here, it came out in the 50s or 60s. Schelling had this idea, they were interested in racial segregation in cities. And the question is, what accounts for this really heavy segregation we see in the model? And there's a lot of reasons you can explain this. So you could go through and do the history of a city and figure out where people put highways. He was an economist, so he wanted to see what kind of choices people make. And so he made a very simple idea. He said, let's assume that there's an abstract space. He actually did it on one dimension. The models have evolved to these two-dimensional models. But let's imagine that people exist on a space, and people have only a very simple rule set, which is that I'm either happy or I'm unhappy. Those are the two conditions that people have in their head. I'm happy if my neighbors are like me. Some proportion of my neighbors are like me above whatever threshold we set. And if they're not, I move somewhere else. I move to any random open space. So that's it. Like that's the only, and it's a completely immediate decision. Like there's no history, right? There's no other background. It's just exactly what's there. And so then you say, let's imagine randomly throwing nodes on a network or on a grid. And in this case, I'm going to show you this program in a second. It's NetLogo. But in this case, the grid is coded by the happiness of the agents. And so here we have orange agents and blue agents. And if the square is solid, then they're happy. At least 30% of their neighbors are like them. And this wraps around, so that neighbor's over there. If it's an X, they're unhappy. So in this case, this agent doesn't have 30% of their neighbors like them. They only has 2 of their neighbors like them, and so 2 out of 8. And so they would rather go somewhere else. And so you let this model run, and it turns out that people self-sort into these really segregated neighborhoods. And it's kind of cool because you might expect that a threshold at 30%, that you would get, up to 70% of my neighbors could be different from me, and I'm perfectly happy. But in reality, what you end up getting is many, many people who have 100% of their neighbors that are exactly like them, because they're not unhappy with it. There's no positive selection for diversity. There's just an avoidance of being completely isolated in your own set. And you can change the setting. So in this case, little things you might not think matter. In this case, we started with about 2,000 agents out of a 50-50 grid, which is a pretty high proportion. If you make a smaller number of agents, do the same thing, you still see segregation, but not nearly as high. That's because one of the hidden rules in this particular simulation is that having an empty lot next to you is fine. Right? And maybe that's not a rule you think is good. Maybe you want, so that's a decision. But it's a decision that this programmer didn't make actively. It was a decision that emerged out of the limitations, or if you will, the exhaustiveness of the rule set. The rule set you give your agents are exhaustive, whether you mean them to be or not, right? And so this is how these things generate. Now, if you ask for lots of bit, of course, you get more segregation, and it's kind of fun to play with. One of the tools that we're going to use, or that you can use for this, is this NetLogo program. NetLogo is an agent-based modeling simulation platform, and it's mainly useful for illustrative sort of toy models. There's a nice set of tools built into it for you can link it to data, and there's an R version of NetLogo so that you can do some programming in data set. But this is the Schelling model, and so what's nice about it is it's a Windows interface. You can just set it up and go. And if you do setup, you can tell it what you want. So in this case, the density is 95%. If I wanted a less, I could say, give me a lot of empty set. Because this model is designed about the observed number of neighbors, you need to have a pretty dense set in order to make it possible to have neighbors that aren't like you. And then you can sort of decide whether you want to have most of my friends to be like, or most of my neighbors like myself, or a few of them. I set it up again, and I go once. You could just step through it one at a time. So here you can see initially that everybody is almost, because I set this really high, almost everybody is unhappy, right? And so there's very few people who are completely happy. And if you have a really high set, then it's not the simulation project, is that this, I can't back up in this particular program, but you'll notice that some nodes that are very happy right now, like these nodes, they don't have any complaints with the world that they're in, but their neighbors are unhappy. And so their neighbors are going to move, and when that happens, then they're likely to become unhappy because the situation has changed, right? And so that's the feedback process that happens in these kinds of simulation models. And because I've set this threshold so high and the network is so dense, like these edges, the boundaries between these sets are always contentious. And so what you'll find if you let this model run long enough is that it's just going to keep evolving until you get almost completely segregated settings, right? So you have this, there's as few people as possible that have any neighbors that are not like themselves. Now what Schelling learned from this model is that it turns out that it's obvious that if I want a majority of my neighbors to be like me, that you're going to get segregated settings. But what's interesting is that even if I want, a minority of my neighbors to be like me, it ends up being the case that you get segregation. And so the percent similar observed here, in this case about half, is always much higher than the target. And so this is the multiplier effect that creates segregation. And his point was that this is the, how do I say it, the sequential effect of prior choices aggregate. And they aggregate in ways that are often unobserved and unexpected. And so we would assume that you would get this kind of heterogeneity, but in fact you don't. So it's a nice illustrative point of that. And his point from a social theory standpoint and a social justice standpoint was that it's not enough to say, I just want to have a few of my friends who are like me. I'm tolerant of other people. If you really want to get integration, you have to have more than just tolerance. You have to have some kind of an active push to make sure that people aren't avoiding people who are or aren't complacent with being where they're at. I lost my spot. So, once you have this kind of simulation set up, how do you get it working? There are a few sort of things that people might not think about when you do these simulations, which are elements of your update rules. And so in real life, people act in parallel. My decision doesn't wait for Tom to make his decision. So I don't have to let him do something and then I do it. Each of us is an individual processor. Our heads are running all the time. And so we run things, so the real life tends to work in parallel. But in programming, it might be important or necessary to do things serially. So for example, in that little Schelling model, it's impossible for two actors to occupy the same space. So there has to at least be some kind of a rule to make sure that if I choose an empty space, you don't also choose the same empty space and then our simulation crashes. So it's often the case for a Schelling model, we'll program it serially just because it's easier to do. We don't have to have a decision rule for what to do when two people want the same spot, even though reality is parallel. So you need to think about how the way we typically institute parallelism, in these really big like city level simulations, you actually use parallel processing. But what you typically do to simulate parallel processing is you give agents an understanding of the state at the top of the simulation. You let everyone make their choices and then implement them. And so that is like acting as if it's parallel without having to programming it that way. What kind of update rules do you have? So do you update your simulation randomly, or do you update it in some fixed order? Update it randomly. Don't update it in fixed order, because that's just as a general, that's just my piece of advice. Like, there's very few situations in which it's easy to say do from actor 1 to actor n and just run your loop. But if you do that, then the actor 1 is always the first actor doing something. And if your data happen to be sorted by race or by gender or whatever, then you're going to build in a sequencing effect that you might not have expected. So it's usually the case that you want to say, pick an actor at random, let them do something, and then move on. And again, it's going to depend when you do it. But the key is you need to think through your scheduling behavior. So this is part of the simulation. And I'm going to sound a bit like a broken record, but every time you write a simulation, you just have to remember that you are inventing the entire world, right? So there's nothing given to you. And so any choice you make and the implied choices that come out of the active choices you make are active in the setting. And so if you don't think through them both, something as trivial as the randomization order, then you run the risk of getting pieces that you don't think you have. Do you have a fixed population, or do you have an actual turnover in your population? So this question came up earlier in the day, whether or not you let your actors in the simulation live and die and have births and so forth, right? The obvious point is, well, in nature, people come and go, and people die, and people are born, so obviously I want to have people come and go and people die. It's really hard to get a good demographic situation. So if my interest is the spread of disease, I don't really want to deal with like deaths due to heart attacks and crashes and suicide and 1,000 other things that actually exist in the real world, because I'm going to have to spend 6 months writing a demographic population simulation to get that point right before I can ever add disease to it. So it might be better to say, you know what, I'm just going to assume that my population is fixed for the amount of time it takes this simulation to work, and if people can die from other elements, that's just a random variable on the edge. And so I'm going to say there's an observed death rate in my population, and so those people can't get sick or pass disease, right? And so I'm going to simplify that element and hold the other element forward. Now, if I'm dealing with an HIV simulation in a country level, that's not a reasonable population. HIV moves slowly, right? For COVID, that's a perfectly reasonable situation. And so you need to think through what process moving through your population you want to have. If you do need to do a demographic turnover kind of population, if people need to come and go from your model, then the biggest mistake people make is that everyone ends up coming and going at the same time. So you initialize all your agents at T1, and you assume they have a life expectancy of 50 years old. Hopefully not, but that's sort of something like that. Then you're going to find out that some group of people are going to all die at the same time, and your simulation population is going to look like this, and that's a disaster, right? So you need to make sure that you seed your population with an actual age distribution, as opposed to everyone having age 1 when the simulation starts, right? Most simulations, and I am, as you're going to see in a second, this is the pot calling the kettle black. There's always more things in reality than you can put in the simulation. And there's often more, so the key element of the purpose of the slides is to think really careful about the values and the number of parameters that you're going to need in your simulation to answer the question you want to answer. And you want to identify the minimum possible number of parameters, right? Because every parameter you add multiplies the number of potential state spaces your simulation can go through. So if I have 2 parameters that have 5 values each, I have 25 state spaces that I can run it through. If I have 3, then it's 25 times 5, it's now 150, right? So you end up with this massive sort of increase in the number of parameters you can do, which doesn't seem like a big range, but it will be a big range. So you need to really be careful of that and make sure it moves first. The value of parameters is spend a little bit of time thinking very carefully about what region of your parameter space is interesting. It's often the case that if there will be values of your parameters for which, logically it's infinite. So you can have like a disease spreading parameter that could have a value of 0 or really, really low, or a value of, the 80% probability that if I have the disease, someone next to me gets the disease, or 90% or 100%. But those are uninteresting, right? So at that end, if there's some bug that goes into the population that has an infectivity rate of 80%, we're all dead. Like we all have it. And so you don't need a simulation for that, right? But there's some range of parameters for which the behavior is interesting, and you can learn something from it. And so spend a little bit of time thinking through your parameters one at a time, and not wasting your time focusing on that area where the pieces are known. You want some areas of your simulation where the pieces are known to check the code, right? So you want to make sure that when I set the disease transmission probability to 0, nobody gets sick. I'm going to say that again. You want to have parameter sets in your model that you can turn the knob to 0 and get an answer that you know is going to be that answer. Because that's how you check that your simulation is right? And so, for example, if I'm doing a network simulation, I will, for a disease diffusion, I will often test it on a pure Erdos random graph. Right? That's not an interesting structure to me. My whole career is built around the idea that those random graphs are kind of useless. But the math is really good on those graphs. And so I can run my simulation over that graph, and I better get an answer that's really close to what the ODE would predict. And if I do, then I'm less likely to have a bug in my simulation when I add something that I can't run an ODE on. Right? And so these kinds of gut checks are ways that you make sure that you have what you need to do. All right, so those are all the baseline sort of things that have to do with any simulation. What about network simulations? We like to think about network simulations in terms of simulations on networks, simulations of networks, and then the joint simulation of and on networks. Simulations on networks are usually something like a disease simulation. I'll start with a fixed given population of nodes or some graph that I care about because of the structures as it is, and then I will ask how something moves across those agents. It could be a disease diffusion, it could be an idea diffusion, it could be awareness of things, right? So, but essentially your agents are constrained to interact with the other agents in the network by virtue of the structure of that network. And so these end up being pretty simple simulations because the network is a fixed object. You deliberately aren't allowing the network to change, or if it's changing, it's not changing as a process of feedback. And so you might have observed elements of the network that you can look at from side to side. And again, disease diffusion is the archetype here. Simulations of networks say, well, where do networks come from? I have a series of behaviors. Agents move around randomly in the population, and I say you let them bump into each other, and if they bump into each other, there's some probability that it forms a relationship. So you have to set the rules for how they move, how they bump into each other, what happens when they bump into each other. Is it an agent? Do they need reciprocity? So there's all these kinds of things that have to happen. These are, in general, when you think about how these things work, there's arguably two broad categories of effects in these types of models. The first is an exogenous effect, that we put actors in the same space. So we might have in our mind something like a neighborhood. So then if people have a neighborhood, then some people work, some people live next to each other, some people have dogs, right? And so you can think of things that would bring people into contact with each other. Those are exogenous to the friendship formation process. Then we have some endogenous features, such as a friend of a friend is a friend. And so if, Madeline and I become friends, then it's likely that because Madeline knows Lane, that Lane and I will become friends. And so we can build that into the model. And we have to decide what that probability is like. And then, of course, in most if you have a realist system, most of these things are happening simultaneously. And often it's whatever's moving on the network is changing the formation of behavior of the network. So for example, if you're doing a disease simulation, this is an example I'm going to show you in a minute, it might be the case that if you and I pass a bug to each other, we both become sick, well then there's a reason for us there's no risk for us infecting each other, so we may as well hang out with each other, right? We both have COVID, we'll sit in our room and be miserable together, right? It's perfectly fine. But if, on the other hand, if I discovered I have COVID, I'm then not going to come into the office. I'm going to move away and make sure that I don't infect anyone else. So this kind of a model allows people to have a feedback process of the of and the on. All right. Some perhaps non-obvious contrary points. Think a little bit carefully about how you configure your network simulation to either keep it within theoretical bounds or within reasonable empirical bounds. Some simple ideas are things like degree constraints. If I have a network formation model where I'm saying people are going to form friends due to homophily or due to, say, transitive closure, do I let them have as many friends as they could possibly make? Or is there some constraint on social energy that people have? In most realistic settings, we're going to expect some kind of a constraint. So it's going to be the case that I can't be friends. I love you all, but I can't be friends with all of you all the time, right? So on any given day, I might be able to interact with, say, a dozen people. And you need to figure out what that threshold is, what's reasonable for the kind of populations you're dealing with, but think through that process. So is it the case that there's a constraint on the upward side? And that's, if there's not, you might have this problem getting these kind of runaway configurations, that if a friend of a friend can be a friend, then any person who anyone's connected to is at risk of being folded into this clique. You'll get this runaway process where everyone's connected to everyone else. Another question to keep in mind is agent memory. Do your agents have a memory or not? And so most simulations, the one that I just showed you, for example, and flocking simulations and a lot of these things, are Markovian. The idea is that the state of the system at time t predicts the state of the system at time t plus 1, but what happened at t minus x is irrelevant, right? So agents have no memory. That's computationally very useful, right? Because you don't have to then carry a memory with your agents. And so that's the real reason we do it. But you need to ask yourself whether that's harming your situation or not. If you're doing a romantic network, it's probably the case that I'm not going to form a relationship with my ex again, right? Once you break up, that's a really hard relationship to reignite. It's not that it never happens, but you want to be cognizant of why it happens and when it might happen. So in that case, you know, the having already been dumped by this person is an attribute that they now have is specific to me, and so I'm not going to go back for a second round of humiliation, right? So this is sort of the model that you want to make sure is built into your simulation. Now, it might be the case that you don't care about that you think that, you know, the memory process is epiphenomenal. It's really the case that once you break up with someone, your friends tell you what a jerk they were, and now you know have a new information about the fact that none of your friends like your ex, and so that it's irrelevant that you want to be back with them again, right? So it's a process that you want to think about and figure out that's in your set, but don't do it. You know, do it purposefully. That's the idea, is to make sure that you have a good sense of why you do it and what's there. So if there's I update this presentation depending on the year and what's happening. So there's a bunch, we've done this now many times, and these are all different kinds of work that I've done over the years, and I'm happy to talk about any of them. But I'm going to talk about a few different case studies next that are a little different than these. But this does give you a little bit of flavor of some of the work I've done, and you know, there's lots of other work that other people have done. So this is a very selective set. Questions or comments about sort of the general process before I jump into some of these case studies? Tom?
I've been trial by fire simulating for the last year, and I just want to add one thing. I think all the considerations for setting up the model are spot on. I think one thing that caught me off guard, I've tried setting up simulations and thinking about those things, but sometimes there are a wide variety of tools out there to help you get started with simulations, right? But some of these assumptions, like presenting population replacement, stuff like that, there are baked-in assumptions to how those tools are set up. And sometimes depending on if you're having a question, the kind of population you're trying to simulate, it may not align with the pre-existing tools and how they're set up. And those tools may be more or less amenable to modification. And we, in work I've been involved in last year, I kind of both extremes. One, the tool's not set up for what we want to do. There's a ton of modification that's being involved. On the other hand, we've recognized the limitations and we specifically designed our projects with those limitations in mind. I think, gravity toward pre-existing tools, right, is very compelling because there's so much done for you. But if you're going to go that route, make sure it's easy to ignore those considerations listed beforehand. And you want to remember that you want to go under the hood of these tools and make sure that it is covering the bases that you need and that how willing are you to compromise? I think another thing with I was talking about barbecue yesterday, right? But in the same way you were saying about primary combinations, compromise. Sometimes when you're studying populations, there are compromises. For instance, you might be interested in a certain ethnic group. But I want to kind of echo what Ash was saying earlier this week, that sometimes the populations, subpopulations there just might be so small that you have to kind of collapse them into broader categories. And in terms of discussions like representation, talking about the empirical
one of the points I'll make at the end, and you see here, is that never sit down and write the simulation you want to do at the end. Write a little piece of it at a time. Like you should be, when you write a simulation, you want to write like micro pieces of it and grow this thing and run as a code base from, can I generate a network that looks like a real network? Can I get things to spread across a diet, right? And so it's like mind-numbing. Instead of sitting down and writing from top to bottom a micro simulation of evacuation routes in Portland, I'm going to make sure that I can figure out how cars can move on a road and what it looks like when the road closes. Like it's very simple elements to start for the pieces and move on. This is an example of a question of using a simulation to answer for me a theoretical question, which is. There's this, in most of the bacterial and sort of disease world, we're used to thinking about simple contagion, that if I have the bug and you haven't built up any resistance to that bug and we're in contact to each other, then the disease can pass. And it's really a dyadic connection process. Well, in social contagion, Damon Santola and Michael Macy came up with this idea of complex contagion, that I only adopt a new behavior if at least K of my friends have also adopted this behavior. And so there's some element, and this builds directly on the idea of thresholds that Tom Work talked about earlier before. And so we wanted to think, well, it's kind of interesting to have this notion of complex contagion because the people who have two friends who could have adopted it are not evenly distributed in the population. So there's a heterogeneity in exposure to the very routes that are possible to have something like a complex contagion move through the population. And this little graph is an illustration of that. Bless you. If it's the case that these two adopt the network first, then it would be impossible for three to adopt the good at time two because only one of three's, this person's, the red node's partners has had the disease. So the only place the idea, I'm always thinking about disease, the only place the idea can move is to two, but once two does, then three can. But then it gets stuck because in this little pocket, there's never a chance for two outgoing edges to leave the population. So complex contagion seems like a very simple idea on its very first sort of notion, that at least two of my friends have to have the bit before I can have the bit. But it turns out that there are some pretty strong constraints built into the model by virtue of the network structure. And so what we did is we said, let's imagine that we just seed the population with pairs of people that have the good, and then ask how likely would it be for those bits to go out into the population and spread throughout the network. And in this case, you can see that the nodes are colored by they're likely to adopt. So the first phase is the yellow and then green and then red and blue and pink and white. And these nodes on the edge never get it because they don't have any two paths to the people to this set that's already infected or already carrying this belief. And so this kind of a constraint happens all over the network. And so we just do this over and over and over again and ask what's the ultimate distribution of adopting in this population? And it generates this really interesting bimodal distribution. The vast majority of new innovations in the idea space here fail. They just don't ever go anywhere. But you very rarely get these middling sort of adoption sets. Because once you cross over the threshold where there's enough of the people that have two of them, you get everywhere. So the structure of adolescent societies are such that most of the time a new idea introduced that has this kind of a adoption set won't ever take off. But every once in a while, it takes off and it will always go everywhere. So going viral is a feat, if you will, of this set, is a feature of the contact structure as much as it is a feature of whatever's going through the network. Now we're playing with this, trying to think, well, what happens when you start instead of, one of the assumptions here was that I started with two connected nodes, but you could imagine starting with two disconnected nodes. We didn't start that at first because the only way two disconnected nodes could infect the third is if they share that person, right? So as an initial starting idea, it's actually hard for that to happen. But that's the set. If you then ask, what's driving this in the underlying variance of the different populations, it turns out that it's the transitivity rate, right? So you have to have a fair amount of some kind of closure in order to get the set, and that's what this curve is. But you have to also have lots of multiple routes in the network. So structural cohesion is the thing that's really driving the overall set. You might think that when you have really high transitivity rates, you would end up getting lots of spread in a complex contagion, but you actually don't. And that's because if you have really high transitivity rate in an adolescent network, what you really have are disconnected subgroups and very tight clusters. And so the bit will get stuck there. It won't find its way out. So this is an example of using a simulation to really understand what on its face is a very simple sentence. The sentence is, I need at least 2 of my friends before I adopt. Well, that simple sentence implies something for the structure of diffusion in the network. Please.
So, like, putting that into context, like you think like the tripod situation, right? So the influencer probably had like followers. They were all connected because they were all following that same person.
Right. It's probably even stronger than that. I think that Google, YouTube, TikTok, they're not sending the ideas to random people. They're sending it to people who share exposure to similar types of others. And so they're using these very ideas to construct who sees the bit and help it go forward. So the underlying promotion algorithms are probably building on something exactly like this. But you're exactly right. In order for it to be taken off, you have to have at least multiple people who see it. Now this was part of the reason that, for those of us that are old enough to remember, that Apple made all of its products bright white, right? Because the whole point was that if you're wearing a mic that's black, you can't see it. But if I have white earbuds in, you can see I'm wearing it together on the bus. You see all these pairs of white earbuds out there, and so you get the fact that it makes it visible. And that was exactly that was an explicit reason for why they did it. They didn't make it bright pink because that was ugly, but white was visible and not ugly. So there you go, right? So that was exactly the idea. All right. Another example that has a little more feedback process is this idea of sustaining beliefs. And so we have a series of models here where we said we have our agents represent people. And the rules are 2 simple rules. Agents adopt beliefs from neighbors stochastically. So if you believe something, I also believe it with some random probability. That's a weight, and that's a parameter of the model. But at each time step, I sort of care about that belief a little less, unless it gets refreshed. The logic here is something like practicing a language, right? So that if I learned Spanish in high school, but I don't use it anymore, right? So it's gone. It hasn't been refreshed. And I think this is a not unreasonable model for conspiracies, for religious beliefs, for other kinds of political ideas, that some of them are activated and reactivated. And if they're not reactivated, they fall away, right? No one really cares about Hillary Clinton's email anymore because no one talks about it. It's not in the set, right? So it's not out there. And so what does this look like? We imagine that process, we let it go on different kinds of networks, and as you'll see from most of my simulations, for me what's interesting is how that kind of a simple behavior model differs across different macrostructures of networks. And so we let this happen on a set of school networks, and you can see that there are some networks for which it's really easy it's really easy to sustain the belief, even in the face of forgetting, because the network structure is different than in others. And so this is not a great illustration, but the point of this slide was to show that despite the fact that in each of these simulations the parameter estimates were exactly the same, the network structures between the two had a greater or lesser what we refer to as carrying capacity. And the thing that seems to be driving it is this average node connectivity. So the structural cohesion of the underlying network, if you have a strongly cohesive network, these ideas keep in circulation. They keep moving. And by virtue of keeping moving, they keep activated, and the belief never dies away. And so that's the thought on that front. Now those are very sort of, these network-based simulations. I have another slightly more complicated simulation in trying to understand how inequality is sustained across groups and populations. So in this case, we take a very simple social exchange game and we play it with homophily. And so the idea here is the population of actors who play a very simple exchange game. And exchange games are used in social science to represent social interaction sets. So we might care about when a cop stops a robber, but from a social exchange standpoint, that's just a police, that police interaction can be thought of as a high stakes exchange, right? And so everyone's exchanged in goods, and so we can abstract all of these different kinds of exchanges, police or teaching or marrying or whatever, and just say it's a game, it's a simple coin flip. So agents have 3 attributes. They're in a group, they have trust for their own group, and they have a bias, and they have trust both for themselves and for others. and they've accumulated some wealth or some bout of good in that particular set. The key element is that group sizes differ and trust is dynamic. And so wealth then is an outcome of each interaction. And I'll show you exactly what I mean by that in a second. The rules are really easy. Pairs of agents meet randomly. Each time we meet, we flip a coin, and we flip that coin that's weighted by how much we trust each other. And so if we trust each other a lot, we're likely to get a positive interaction. If we don't trust each other a lot, we're likely to get a not positive reaction. So that was a simple way of saying what this is. So this is what each agent faces. And so each agent faces a trust situation, right? And so when we first meet, there's no prior history, and so I don't trust you anymore or not. It's just whatever's there, right? So at the initial meeting set, we have some probability of agreeing with each other or not, and so that's a baseline trust, which is here, right? Here. And so that baseline trust, beta, is at some level, and it's fixed on this set. And then at each interaction, if I win, then I trust you a little more, and so then our weight goes up. So if we have a positive interaction with the police, then it ought to be the case that the next time I interact with the police, I feel better about them. I trust them, and so the interaction goes better. The goal of this set is to try to inculcate an idea of sort of a self-fulfilling prophecy or another kind of feedback process of where if we like each other and things are going well, it continues to get better. If we have bad interactions, we distrust each other, things get worse. Excuse me. But we want to put this equation describes, so we have an in-group baseline trust, an out-group bias, and this thing I call a bias decay, which is easier to see here. And so for any two groups, and this is set up in this case, we have in-group for group 1, in-group for group 0, 1 to 0, 0 to 1. So this is you can see this is a two-group model that we have ended up building here. My thinking is that people learn from their interactions. And so if we have no interactions, it's my bias that governs how I believe. So my in-group might be, I have a pretty high sort of sense in which I trust people who are like me, but I trust people who are not like me less. So that's all this is saying. But if I get a lot of experience, eventually my bias goes away because I don't need a bias if I know you. If I've interacted with you many times, then it's the case that I can just use my knowledge and not my bias. And that's what this is. The model's worse, actually, if I get rid of the bias decay. This is a generous assumption for my agents. Excuse me, I apologize. I've been talking too long this week, but you probably are bored of hearing me talk this long. So whenever my voice is problematic, your ears are probably worse. So, but imagine this thing that works this model works kind of like this. So in the simplest possible situation, right, there's a mixing matrix of zeros and ones. They're all the same size, and the parameters are all the same. And so each time we meet, we flip a coin. And when we flip a coin, we get a random accumulation. And I believe that people are generally good, and so it's a positively biased coin, right, in this particular case. And so on average, about 60% of the time, when I flip a coin, it'll be a win. 40% of the time, it'll be a loss. And so that means that 60% of the time you move over this way, and then you get up to like 80%, and then 90%, and so forth. So most of the time, you get this positive increase in exchange. So each line represents a pairwise exchange, so one I with one J. And as you expect, most of the time for each person's, it goes up. Not always. The world is a random stochastic place, and some people, once they start losing, right, they continue to lose. And so this pair of people don't get along very well. Right? Now, if you then aggregate up across that network, you see that in this particular case, everyone's making money. Everyone's doing fine. Wealth is whatever you want to call it. They're doing well. Bless you. Now let's imagine that a little more realistic situation where we have equal-sized groups, right, and they both have the equivalent trust for their own group and equivalent distrust for the out group. And so in this case, as you would imagine, the pairwise interactions are much more positive in group. So we get an in-group pairwise interaction is positive, in-group pairwise interaction is negative or positive, and the between-group interactions are negative, by and large. I didn't set this parameter so huge that it's completely swamping, but you get more negative interactions between group than in group. And what you see is, again, positive overall effect. but not as strong as it was before. If you pay really close attention, you'll see the axes dropped a bit, and you get a slightly more shallow slope. Personal level accumulation does that. Now let's make a more realistic situation and assume we have a majority and a minority group. So zeros are our majority, 1 is our minority, and so there's a differential group size. And again, if we said everything is equal, same kind of process, you get no difference, and so everything is fine. Then we said, again, each group trusts themselves the same, and they distrust the outgroup the same. So this is a very generous model from a social standpoint if you're modeling, say, race interactions or some such. And in this case, if we run the model, we see the same kind of dyadic effect. We end up with lots of in-group effects that are positive, lots of in-group effects that are positive, cross-group effects are negative, cross-group effects are negative. But then if you look at the accumulation across the population, you'll see that this situation leads to much more negative outcomes cumulatively for the outgroup than for the in-group. Why is that? It's because group size ends up accumulating. And so if you think about what this adjacency matrix actually looks like, the minority group has fewer opportunities to win than the majority group, and the minority group is faced with massively more distrust in the population as a whole because of the differential in group size. And so you get this amazing multiplier effect that even though everyone is behaving exactly the same, it has a much more negative impact for the minority population than it does for the majority population because of the differential access to winning. And so there's just a sheer numeric result. So I like this model because it allows us to think through how you might fix a process like this. So if you're starting with something like this, where you have the simplest of possible exchange models, and the baseline sort of interaction rate is going to lead necessarily to structural inequality because of the differential opportunities to meet, what do we have to do to fix it? Well, one solution would be to say, let's buy black. Let's have a campaign where we increase the within group sort of winning rate and keep everything else the same. And we could do that. It ends up being the case then that it has to define a different set of probability spaces. So now you have one curve for the in-group set for whites and the out-group set for blacks. But notice that at time equals 0 here, we've just set the win probability within group much higher than the times 0 win probability for the majority base. You can play these kind of games to figure out what it would take to make it win, and you have to really crank up the in-group set in order to get a match with the majority group set. And so what I think this tells me is that if you want to alleviate structural inequality that comes from the baseline differences in group size and the opportunities for making positive or negative interactions, that if you're going to do it, you're really asking a minority group to do a lot to pull itself up, right? They have to really overcome, essentially, and you can work out the math of this, the size of this coefficient has to effectively be proportional to the size of the difference in the two groups. And in order for that to happen, the smaller the group is, the harder you would have to make them work in order to succeed. And that strikes me as probably an unjust effect. And so we might instead want to focus on some of those off-diagonal elements instead of the on-diagonal elements. Right? So that's the kind of thing you could learn from these models that you wouldn't do otherwise. All right, one last case study that I think is kind of fun, which is more relevant to this group than to the sociologists, is and this is meant to be a little more realistic in terms of the way these models work. In this case, what we're doing is we're trying to understand disease spread, and we want to have a behavior feedback process with disease spread. And so we're running, our environment's going to be village or rural networks. We're running it over observed networks. People have a full slate of demographic, economic, and activity sort of analogs, so we're going to try to treat people as if they're real critters as best we can, given the data that we've observed. And then we're going to layer over it two kinds of models. The first is a biological model, which is a simple SIR infection model, and we use two cases. One is HIV and one is COVID as the kind of examples we run. And the second is the social behavior, which is that agents are nested in households, they have jobs, they're engaged in neighborhoods, right? They have all these things that are engaged. And the general process is that we have sort of simultaneous updates, so everyone is sort of living their lives. And so we're trying to build a pretty realistic model in this case. This implies a huge parameter space, and that's why I'm showing this example, is that if you want to make sense of what this is, we have disease parameters, we have network parameters, we have actor constraints, And it's really easy to walk yourself into situations here that are nonsensical. And so in order for me, when I deal with a problem set where I have lots of, when the event is a probability and I have lots of variables that can feed into that event, I almost always convert it to a logit equation, because that way I don't have to make sure that all of my little tiny bits add up to less than 1, right? I can just let the logit equation do that for me. And so almost all of my parameter space models will end up looking something like this. And what this is doing is this is not an outcome. This is literally a map of the parameter space. So this is what's saying, like, what's down at the level of an individual dyad, what's the likelihood that if an infected comes in contact with a susceptible, that at this level, biological level of transmission, what's the likelihood that it would be transmitted? And that's conditional on the strength of the tie across the columns, on the whether or not ego themselves are symptomatic across the rows, and then within each panel, the number of their, the proportion of the population that is infected, right? And then within each panel is a proportion of their peers that are infected. So this is a 1, 2, 3, 4-dimensional space I'm trying to display here on this, 5, I have a color as well. So this is a 5-dimensional space I'm trying to display on one set. And so as you might imagine, it's a little complicated. But as you think about it, this isn't a particularly complicated simulation yet. Like, what I'm showing you is actually pretty easy. In this case, we have, essentially the probability of transmitting the bug is higher for strong ties than weak ties, generally. And that people are making choices depending on each of these elements. So in this case, we're saying there's about a 0.7 probability that a healthy ego with a healthy ego who's connected to a person with tie weight 1 and no infection in the population and no sick friends, right? If they happen to be sick, they're highly likely to pass it on to someone else. As more of their friends become sick, they're going to essentially pull themselves in and interact with other people less. That's the way this simulation is set up. And so they're unlikely to pass it because they're going to be self-aware and they're not going to do anything. If they feel sick themselves down here, then they're going to stay home and do even less. So the difference between this 0.8 and this 0.35 is a self-selection away. I'm saying I'm not going to infect anybody else because I feel like crap. I'm going to stay home. But I can, and that's easy for me to stay home for my weak ties, but I still have to stay hang out with my wife, right? So my strong ties over here, actually, they're at higher risk when I feel sick because I can't avoid them as easily. And so that's why you see this going up with tie weight. I might care about them more. I might wish I didn't make them sick. But by virtue of this correlation between the strength of the tie and the inability to leave strong ties, we expect that it's going to look like this. Then there's a population, sort of independent population effect, that if I look around into the world or listen to the news and I don't hear a lot about people being sick, it might not be salient. If I know there's a pandemic going on, it might really be salient. And so I even tried harder to protect myself. And so this is like sort of what this world looks like. This is the world we've defined in this case, and it's just these 5 dimensions. So I try to give some sense of that. And then we run the SIR over it. And you get these kinds, this is just a sort of a cautionary tale on how quickly you can get lots of different results and you have to parse them. Right? This is what no social feedback at all looks like. So I've had one parameter set where I've set the coefficient to 0, so the pure sick coefficient is to 0, the population coefficient for a 0 is sick, and then in this case there's no symptomatic effect. So this brown line is what my biological infectivity rate would imply. So everything is effectively relative to that. And so then what I do when I go through and think about how these different features matter, I would go through and ask, well, compared to a biological only model, if people are really receptive to the population being sick and they're really receptive to their peers being sick, then you get a much lower effect. And you can then gauge how that works. And so this is the game we're playing with this model. And this model's not done yet. This model's in process. But this is what we're trying to do is figure out, effectively, are you better off advertising, the population model would say, if the probability of people not engaging, not passing the infection, is sensitive to the number of other people in the population that are sick, then maybe if we just advertise the extent of a pandemic, then that would be all we have to do, right? That's what this difference across the columns would look like. In this particular simulation, it looks like the difference across the column doesn't have a huge effect. And so, maybe my parameters are wrong, maybe my theory is wrong, but that's the kind of thing we're going to interrogate, is try to figure out, well, how strong would the population slope have to be before my awareness of the population would make it likely that I would stay home. And so these are the counterfactual games we play. Notice what I'm not doing with this. I'm not fitting it to an actual disease somewhere, right? So although there are realistic elements in this simulation, this is not a realist simulation. I'm not trying to predict the next pandemic. I'm trying to predict how the behavior would be different if people were more or less reactive to local effects versus global effects. All right, I'm out of time, I think. But in the slide deck, there's a series of pragmatic points and software you can use. I really do recommend, if you're just getting started in this business, to play with NetLogo. It's it's not quite as shiny and new as R is, but one of the nice things about it is that it has all of these models built in there. And I wish I could go down here a bit. And the NetLogo language is English, right? And so you can actually read it, right? It's not these weird functions or whatever. And the simulation code to run a shelling model in NetLogo is only 80 lines long, including the comments and all of the display things that are there. So the actual model itself is modular. It's very easy to set up. If I want to change elements of these things, I can go in and do it. There are network models already built into NetLogo. So this is a diffusion of a virus-like simulation across a simple model. And so you can set up the different kinds of curves and ask how a disease might move through a very simple toy model. It has all of these things built into it. So it's a very good model to learn how to write a simulation. And they now have some production code if you want to go into RCiena, or not RCiena, NetLogo, and you can tie it to data or whatever else you want to do. Right? So there's lots of nice pieces that are in there. They also, because it was generated with the idea of being a teaching set, they have all kinds of different elements built into the information for it that tells you what it is, how it works, why it's being used, things to notice, right? So it's a very nice teaching tool for helping yourself understand how simulations are built. And if you want to go in and take the NetLogo model, for example, for shelling, and instead of having 2 colored turtles, you want to have 3 colored turtles, you can just go in and literally, where did this go? On the setup. Yeah, so in this case, their color's either white or not, right? So so here you go. So I can have the number that are 1 versus the number that are the other. I can just switch that around. If I were to add, I believe this will work. I'm going to try it on the line. Let's imagine that I would say, well, I'm not going to do that, never mind. But anyway, you can go through and you can change these things really easily and with just a little bit of effort. All right, I am over time, but questions or comments? Because I'm speaking next, I'm only stealing from myself. So. I encourage you to play with simulations. I think that one of the things that's great about simulations, even if you never publish anything on a simulation, is that the process of coding it makes you think. It makes you a better thinker I think, it's redundant, I guess, but I think you're a better thinker and you're a better theorist if you have to write down and force a machine to do what you think the world does. You'll quickly discover that your understanding of the situation is probably inadequate. And there's a whole bunch of things you have to add to it in order to make it even work, let alone work like you think the population works. Please.
Okay, so this is not a technical question, but I do wonder broadly, and I don't feel like you already spoke to this, why is agent-based modeling, simulation modeling, how is it really developed or grown out of network analysis? Because it's not always going to be about these direct people-to-people connections. I've seen simulations that are not based necessarily on people, and so I'm just curious, what's that evolution?
Yeah, that's a great question. The main question is that most of the agent-based modeling on networks came out of the problem of processes on networks. And the point was that we never have data on processes on networks. And so in order to understand things like the spread of something over a population, now Tom's gone out and collected actual data about adoption in the real world, But for lots of settings and for lots of things you want to do, you just can't get the data. And so people started doing simulations because the data were just so bad. And particularly in the early 80s and 90s, when the HIV epidemic kicked off, and we knew this was a sexually transmitted disease, and we wanted to understand what the different effects of different kinds of network structures were, we were shooting in the dark. And so the tie between agent-based models and networks largely came out of that hole in the data set, in the data side. Once that happened, people were like, wait a minute, there's a lot here. We could do something with this. And so these two populations of agent-based modelers and networks things started differently, but I think they really crossed over when people came to recognize that in order to answer something like the HIV epidemic, we needed to understand at this micro level how these different transmission choices would aggregate up into a pandemic. Like that feature and sort of pushed the modeling direction really forward. And then once those models were done, people recognized that you could use it for ideas, you could use it for beliefs, you could use it for polarization, you could turn it on in the network itself. And so then it sort of just, the networkers just adopted the ABM framework in order to answer these interesting questions.
And where did the ABM framework, what discipline did that come out?
Yeah, that's a much more interesting, I don't know if it's more interesting, but that's a great history. So I don't know it particularly well. I have a very biased view of it because I'm coming of it from the network side.
So it was separate from.
It was separate.
I thought maybe that it had kind of evolved from the
No,
network.
they were parallel movements,
Okay.
and there were lots of systems things happening. So traffic and nature simulations. So there are all these beautiful. You probably did this in junior high, where you have birth rates and death rates and some amount of things, and you look at population booms and busts, right? So those kinds of models were coming out of the 50s and 60s, and then the Schelling models coming out of segregation, and some of the stuff that Coleman and others were trying to do. So there's a whole series of folks who are thinking about other kinds of social mobility processes that the networks folks picked up. The best agent-based modelers these days are probably not in networks, that they're really dealing with things like disasters and traffic and military simulations. And so those folks, they have network pieces built into them, but they're not necessarily network-centric.
And so they were looking at like system science.
Yeah. Yeah.
Okay.
And the disaster people, I mean, if you think about it, like if you want to plan for disaster, you can't wait for the next earthquake, right? And so my favorite agent-based model actually is of the earthquake model for earthquake and tidal wave models for different cities. And one of the things they discovered was that if you make some reasonable assumptions about how people can evacuate after a warning for a tidal wave, that everyone getting in their car is the worst possible thing that could happen. And for some people, what they should do is walk uphill, and they shouldn't clog the road so that the people who are there are not. Now, what the model shows is that from an agent-based standpoint, you can really, like, at each actor make these choices. It also ends up being a prisoner's dilemma situation, because although the optimal choice is that everyone should let the people who really need to drive, and everyone else should run on foot, each individual wants to get the hell out of there as fast as they can so they don't get stuck, and if everyone does it, you end up with the traffic jam and everyone dies, right? But that all came out directly from the agent-based model side. Please.
Yeah, I was wondering, in the case of the minority versus the majority group, and on slides I was saying that what is it called? Something related to based on the trust is based on prior success.
Right.
And I wonder whether that also entails that memory is taken into account.
Yes, so in this case, exactly. I've built this cumulative win-loss record that people carry. And so that's what that curve is actually defining, is the memory function. It's like do I trust you? Well, initially no. Initially it's at this baseline set, but the more experience I have, I move up and down with you. And so you might be the kind of person that and there's a lot of unrealistic things, of course, but one of the unrealistic things is that it's just a summative memory. So it's the fact that we've, like if you and I are going back and forth and you cheat me one day and you don't cheat me the next and you cheat me one day, it all balances out to zero. That's probably not realistic, right? It's probably the case that if you're not reliably trustworthy, that I should trust you less, right? But that was one more parameter module I didn't want to screw with at this point, and so I haven't gone there yet.
Right, because it is sort of it is kind of like a cumulative.
Right.
That also keeps updated based on why.
Right, And instead what you could do is let's just keep a weighted function of the last 10 interactions, right? And say that, you know, if and you might, your argument might be that the higher the variance in those last 10 things, the less trustworthy you are, despite where the mean is, and as virtue of that, I should be a little less trusting. And so that would be a perfectly reasonable model. I don't know how it would affect this outcome. I haven't run it yet, but we can find out. All right, the last session is, again, me. You get to hear even more of me. And what we're supposed to, what's on the schedule is an open session, and to think about the future of network analysis in health. And I have some slides I can go through and talk about, you know, some more, I can broadcast more, and show you what Moody thinks are the priorities that should happen in the next few weeks. But I'd really rather not. I'd rather sort of open the floor and have people ask questions that are burning to you. Some of our experts in the room who have been working in this field for a while might suggest what they think is important, and just have a discussion for the last 45 minutes of this conference to think about where we should go next and what we should do. And so I can go either way, and this is why I didn't put anything hard-coded on the schedule. Because if you want me to continue broadcasting, I'm happy to do it, but you might be a little tired of that. So I'm going to open the floor now and force myself to be quiet for at least 2 minutes, or at least until someone else says something, and we'll see where we go from there. So questions or thoughts? You've now had 4.5 days of swimming in networks. What's the burning question or the thing that's left open at this point that you really wish we had talked about, or that you think you haven't heard an answer toward? Do you want to go next? Please.
Could you talk about what you believe are the most pressing future methodological directions?
I didn't hear the
most pressing future methodological directions.
The question is, the most pressing future methodological questions. There are so many. So I think that there are a handful of things that we're getting really good handles on. So the evolution over the last 20 years, 25 years in Siena, in ergom, in Bayesian ergom models, and other kinds of models of networks, and now behaviors on networks. So we have these AALMs, I can't remember what it all stands for, but essentially network autocorrelation models while you're doing an ergom at the same time. So our statistical modeling of networks is still it's still hard to do, but it's so much better, and we've gotten so good at that. So I think that that's kind of settled. There's a lot of cleanup that needs to be done on the edges of that, but I think that's in good shape. The real problem with that work is scaling. And so figuring out how to get these models that we have for 2,000 nodes, for 200,000 nodes, or 2 billion nodes is something that's a little harder to do. And particularly for people who are interested in the spread of things on online networks, we need to be able to scale. So online networks and other sorts of social media type of networks, they tend not to matter for those of us that care about physical health, but they matter a lot for mental health, and they matter for political health, right? So there's lots of reasons in which we think these large on-scale networks are important, but the kinds of tools that we've focused on are insufficient to deal with those things. There are other tools for them, but they're coarse. They're pretty tough tools. For the kind of world that we work in, and the kind of stuff that we haven't focused on, I think the next foundation is really to go back to some of the ideas that we had originally, which are multi-relational networks. And the good news is that there's a new buzzword for multi-relational networks, which is multi-layer networks. And now that we've put a new name on what it is, people are interested in it again. And so that's good. I'll take a win wherever we can get it. But we started the network field in social sciences started around this attempt to formalize and make explicit our understanding of the really rich tapestry of social relations. And that quickly ran in head on into this practicality bus. And so the goal of doing these rich community studies, the problem is that none of you could get a career by going out and doing a community study now, because you can't afford to spend 6 years living in some town in Midwest Iowa and to write up the sort of features there. We don't have an academic career structure that allows that to happen anymore. But we still want to have that level of detail and understanding. And so finding a way to regularize, routinize, and efficiently analyze large-scale multi-relational networks, I think, is something that's an open field. We have really good theory from structural anthropology and the old theory from sociology and so forth to think about that, and great insights coming out of local networks, work like Mario Smalls and other sort of people who are thinking about the ways in which networks are co-determinative of each other. But I don't think we've built that into our formal modeling as much as we can. Bless you. Nor do I think we need something, I think, and I'd love to hear what David, what you think about this, or Tom, what you think of this, but I think we almost need a natural history of networks, or a natural history museum of networks, right? I mean, the beauty of biology and sort of natural sciences is that it's perfectly reasonable to go out and figure out what new species are there. And we don't really have as much of that anymore, and we'd started to. That's what those big, beautiful diagrams of small, of women in villages were about. We don't have as much of that as we used to. And so I think that thinking about this ethnographic sensitivity in a quantitative, rigorous analysis is the lacuna that I would like to see filled. And again, this is Moody's. You're getting a very biased view on that set. I'm going to start there. Tom, do you have ideas of what we need to do?
Yeah, I mean, obviously, I would suggest that we're going to learn a lot by doing network interventions, right? And then being able to model what's happening to that network over time when we purposely intervene on it. I also think you're right that being able to scale a lot of our approaches is a big challenge. There's been some work with, that large-scale LinkedIn experiment where now you're talking about tens of millions of nodes. And once you talk about tens of millions of nodes, you talk about hundreds of millions of links. And we have really good tools for looking at smaller networks. To get to that scale is a real challenge. So I think those are two big frontiers that will offer a lot in understanding what's happening in society. I also think somebody ought to do a history of network analysis, because the field has fragmented in some ways. There's a lot of different streams, and it'd be interesting for somebody to do some kind of oral history and ethnography of what's been happening. Those are just some ideas, and there's a lot. I mean, we like to talk about the social media stuff. That's a huge trove of network data. It has strong implications for what's happening to people's mental health, political polarization, misinformation, disinformation. Finally, Francis Collins, the director of the NIH, released a statement about 18 months ago saying, we really blew it when we released this vaccine stuff because we never thought about the communication problems. And he was one, when he founded the National Human Genome Research Institute, he very specifically demanded they have a social and behavioral science branch. He said, we're going to figure out what the genome does. We're going to understand these associations. We just don't know how it's going to play out in society, right? And so what you see now, of course, is we're going to get vaccines. We're going to release them. Our assumption as scientists is everybody's going to love them. These are great. It saves lives, right? And then what happens? It turns into a political football. And now vaccines of all types are being questioned. And so there's a lot we can do around network analysis to address very serious societal and, in my world, public health problems that demand attention. And we've got a lot of work to do. And hopefully we'll start to see more funding in this direction because I do think it's a way to address these problems very explicitly.
David? Yeah.
Yeah, I was just going to second, I like the Natural History Museum idea. I would take my kids. but seriously, I've done secondary network analysis for so long that recently I've combined some peer-reviewed methodology. It just leads to questions about what's happening within the context you may not even imagine. So I think combining the mixed methods really is something that we need a lot more of. And then the second thing would be thinking about time. So many of the models that we talked about this week are all panel data. But networks, core processes, the kinds of things we're talking about, how those happen on a much finer time scale that we're not capturing. So we've got network models, relational set models, and how we monitor the changes in relational different aspects of relationships over moment to moment scale. And so kind of combining those with the kinds of models that we have that longer scale changes in relationships or changes in statuses. I just think that methodologically, more
saw another question here. Yeah, please.
Yeah. So one thing I noticed is that presenters use a lot of smaller community level data. I think those are really helpful, like in a program level. I think in my experience in my world with working with federal policy, I think policymakers or decision makers are more comfortable using bigger data. They're a little bit more comfortable in making decisions and those decision processes that happen. So I think, I know surveys are super expensive. I can just imagine if you want like a national survey that's specific for network data, that would be really costly as well. So I wonder if there's, you're seeing a bunch of methods of how to collect data, big data, that are, I don't know, way smarter.
So I think there's a couple of answers to that. I think you're absolutely right. So the scale issue is there. I think that there's a big push now for trace data. So one of the boons that we had was coming out of COVID was SafeGraph and Google for Good. Like these kind of folks were putting out data that they didn't have to put out. Those data that allowed us to look at human movement from one place to the next are inducing networks, and so we can get some sense of at least where people are coming into contact with each other. So for things like communicable diseases, that's a reasonable underlying network. For belief structures, probably not going to help us a whole lot, right? But there are lots of other kinds of traces that are out there. So if we know the bipartite network of what people consume on media, then that's going to tell us a lot about clustering and the range of different opinion dynamics that could be out there. And those data exist, right? So Google has all that data, they're just not sharing it, right? And so we have those pieces. The second answer, I think, is that the world is big, but we don't try to go out and collect, like, you know, when we put a poll for the political events or something, argue about whether it's good or not, but we don't need to survey every person, right? We only do that every 4 years. We sample, and we have a way of sampling which is effective for aggregating up individual opinions. We need better sampling methods for network opinions and find a way to do that.
I want to jump in on that. I totally agree with that. When we were talking about the scaling issue, I was sitting on my hands back here because I work with large networks all the time, and one of the things that often spending a lot of my time doing is actually identifying the relevant subset within the network that really can help. And in my space, we can then do shortcuts like stance detection and things like that to identify that, but having principal network sampling techniques to extract the relevant subset. Because in fact, even phenomena like going viral, you know, you go viral actually in subcommunities. Like, look, there's things that happen. I worked for 3 years on GitHub data. There's things that happen in GitHub data that go viral, but no one else in the world knows about it. Right? But it's a real viral process, and it's a large, super large network. We don't. I'm totally there that we need scaling issues, but you don't actually need the network of everything. You need the relevant network to your research question. And so getting good, we've got ad hoc ways of extracting these relevant subnetworks and making stories about them, and we try to be a little bit more principled about these stories, but it does make me nervous in our work. And so the thing I would interject is, let's improve sampling theory for that.
And I think the beauty of most social networks are they're big, but they're incredibly sparse. Like most human, Dunbar showed a long time ago that most of us live in a very small interactive space. So the number of people that we actually interacted with scales, you know, literally with a hard stop, whereas the population is going up, the possible space goes up with the square. So there has to be a sensible sampling strategy. We just haven't invested deeply in it. Ego networks go a long way. A lot of the processes that we're interested in are ego networks. And so, you know, two-step ego networks might be all we need, but I don't think we've done the work that makes it really clear where we can do that kind of sampling. Please.
I guess I'm curious about, I know at the beginning of the week we spoke a lot about the ethical considerations, but especially looking at online data where private companies can purchase so much metadata, but that's not data you could probably collect or pass through an IRB, nor should you maybe. what is that balance between like the ways in which IRB should adapt, as you know, there's just so much data, or should adapt to what's going on and what you can collect versus like, especially if you want to do pre-bunking or some type of like dispelling mis or disinformation.
Yeah.
That's information that people can purchase, but you can't necessarily pass through at university.
Yeah, I mean, I do think that to some, I mean, and this is a question that I certainly can't answer, and I think that we as a field have to struggle with. My sense is that we've been trying to fight with our hands tied behind our back for years now with respect to this, that the kinds of things that private companies get away with in terms of collecting data, which, you know, aren't particularly harmful, and people volunteer doing all the time, we can't do. And so I would, you know, argue that in many cases, in many sort of situations, that it's the IRB sort of hyper concern with treating all data as if it were, you know, your medical tests, as opposed to, you know, what books you might have purchased or something. I think that there's a lot of room that we need to rethink what the actual risk is, as opposed to the cumulative benefit. Now, I think that, yeah, it's going to be really hard to draw that line, and if you've ever dealt with a medical IRB, they are not flexible people, right? And generally, I mean, I'm sure individually they are, but as an organizational collective, because no one wants to be the person that comes out and says, yeah, do whatever the hell you want, you'll be fine, and then have something bad happen, right? And so, you know, it's always easier to be more, it's always safer to be more and more restrictive and more sort of set. And I think that, you know, we no longer live in a world where people have a reasonable expectation of privacy in every day. You've probably walked through 100 cameras before you got from the hotel to here, right? So this notion that, and certainly, you know, Google followed your phone the entire way. So the sense in which, you know, we are used to thinking about private behavior and private set sort of completely anonymous away, there's this whole range now of activity that is semi-public and certainly public to a certain audience that I think that it would be nice to be able to have some way to, I can imagine a social goods tax on information that says that companies are already collecting this data, they need to find some way to make it available for us to use for public good, or you're not allowed to have a monopoly on that data anymore, right? So that would be a perfect, like, making something, like, I have thought about that idea all of 2 seconds now, but you could imagine that there's going to be some kind of a compromise between private profit and public good that comes out of this. It would be quite useful. I mean, when Mpox first started popping up in New York, there's no way that you know, the dating apps that are already there wouldn't have been, if we had had that data, it would probably be much faster at being identifying what the risk set is for the spread of those kinds of diseases than would be otherwise. I don't even know who's having sex with who, but knowing what the structure of that network looks like lets me know whether or not this kind of a STD is going to be really dangerous or nothing to worry about. And so thinking about those kinds of features, you know, why not make that data available in reasonable ways to researchers to do something? Please.
So another question related to the data collection. I was wondering whether in the network data collection, whether participants can actually have more agency in terms of like collecting data themselves and also reporting data or donating data themselves. So I listened to a presentation. I think that was data donation initiative that took place in Europe, but that was related to the health and also fitness and location data for respondents to donate data voluntarily themselves. So I wonder whether that could help in the network data collection, and also like for the time use data, respondents can document their time use themselves so that respondents have more agency, or like our population of interest have more agency in terms of documenting their network structure.
For those who couldn't hear in the back, that's a great question. The question was about whether or not there's opportunities for data donation. So it would be possible for people to donate and create a public archive of network data. In much the way they do with time use data and other kinds of biological samples, sort of this public science idea that where people are doing citizen science and helping, you know, observe bird watches or whatever. Yes, I mean, you know, I mean, if you would, I think you should start it, right? The hard part there, and this is still an issue that I think that for a public repository of network data, is that if I'm reporting on my reactions with you, but you don't want it in there, is that fair or not? And so it's because it's not an individualized choice it's a little bit harder. Now, the time use side is easy. That's like, how I spend my time is fine. Whether I'm identifying other people while I'm at it or not is still a question. Now, I'm on the liberal side of that idea. I think it's fine. Like I'm not going to, if I, but I think that that's something that the field would need to come to a decision about that we haven't yet. Please.
So in most of the examples we've seen in the past days, we are dealing with the network data where each node represents an individual. I think we've seen some alliances across countries. That was only, I can remember that's not the case. But I work primarily with inter-organizational data, like government agencies and nonprofits working together on social justice issues or things of that sort. I just wonder like what your thoughts are on inter-organizational network and research and opportunities in that area.
Yeah, the good news is that inter-organizational network data is a well-trodden, very well-developed field. So there's plenty of people doing out of it. It's a bias of the people I know and arms I can twist to come here that you're getting mainly individual level data because that's the data we're working on. And there is something of a bias, I think, in health field where we focus on people getting sick, right? So we've been doing this, but there's I strongly encourage you to go check out Journal of all the Academy of Management journals. There's a bunch of work there that's been done on interorganizational networks, and so that's where that work is happening. The main thing about aggregate networks is that a lot of the theories that we've talked about in terms of network formation and dissolution and transmission processes are predicated on the idea that people control their relations. Yes. For organizations, it's a committee that controls the relations at best, and it might be, and it's often variable internal to the organization. So interorganizational networks often make this assumption of a unified organization that is a node, when in fact it's a network within the organization of people that are doing things, and you get a cumulative decision. Right, and so you end up with this weird multi-level network of networks thing that is kind of hard to deal with. Now there has been some great work on that, which I'm just going to draw a blank on because my brain is fried, but on the author that I should be remembering. But anyway, yes, so there is work on this. I think that if you're more than accurate to point out that we haven't covered it here, that is a failure on our part, not of the field. So there's plenty of work out there to be done. The good news is that one of the things that I love about the network paradigm is that it's a transposable abstract data object. And so much of what we talk about is applicable, like it's called community stuff, the transmission stuff, all of this. It's when you start thinking about the theory that drives why the organization changes that you just want to be a little bit careful that, a friend of a friend is a friend, but a business associate of a business, a company's exchange partner of a company's exchange partner, there's no real reason to think that they shouldn't be competitors, for example. John?
Just drop a buzzword for you. Look at organizational theory, the CMU School of sort of organizational network stuff like that. There's a whole bunch of stuff though. There's really simple companies competing with each other and ecological approaches on one hand. Then there's intra-organization looking at formal and informal networks. What's the network that actually makes the organization go compared to the one that they tell themselves about? So like looking at crackers work. I can give you some other references after, but like there's a few buzzwords. That's one. The other one's to get around the complexity of your fact you're actually looking at networks combined with interdependent on other networks. Is this classic interlogic director? You look at who's on each other's boards or things like that, where you can then make where the assumption that there's some kind of actual unitary action going on is a little bit simpler because you're just going to see coordination of the board. And I was thinking to some people have that kind of data here. So that's a classic, well-trodden thing with lots of review papers and stuff that you can then go and dive down the rabbit hole and get into further. And I forget the book you sent me when I went to Jordan. If you ping me, I'll go find the title of it. It was a really nice sort of boards networks piece. But again, it's been a long. Those are two of them. So computational organization theory and the classic interlocking board of directors kind of literature.
One of the things that I would focus on, just the organizational point reminded me, is that the vast majority of our networks are constrained by our schedules, and managers create networks all the time. And so if you have the opportunity as a hospital manager to figure out when your nurses are scheduled, you're creating co-contamination networks of nurses and patients by virtue of the shift schedule. And when you start juggling people's shifts, you're creating random ties across networks, and you're increasing the extent to which the hospital is integrated from a transmission standpoint. That may or may not be good from a worker standpoint, but you can imagine saying, I'm going to have people that only work particular shifts and segmenting that network and creating the opportunity. We built a model, which was ignored, and we can debate whether this is useful or not, for campuses that said you don't have to close campuses down. You can take majors, and you can if you just cut out the inter-major ties and you make students just focus on their core requirements within majors and cut out the general requirements, you cut 90% of the cross-student contamination risk for something like COVID, and you create little mini universities. And that's not as good, right, from an educational standpoint. You want physicists to take English classes, but for a year, it's better than staying home and being Zoom, right? And so you can imagine these kinds of trade-offs. You might imagine I had a dog in the fight and I lost. So, but in retrospect, it might have been better from a learning loss trade versus contamination trade-off to let students have colleges within universities as opposed to just staying home and doing nothing, right? And I think that's the kind of, when you think about what we do when we put people together, we create networks all the time. And organizational networks, managers are network generators. They're just usually naive, unthinking network generators. And it's useful to maybe think about what that projection looks like. Tom?
I was going to say one thing real quickly. There's probably a whole lot of network analysis and very sophisticated network analysis that we don't know that the military is doing. I suspect they do more of this than anybody, and probably more of it than all of us combined.
Yeah, I've seen mapping of the Al-Qaeda network is really good. Yeah,
I'm sorry?
I've seen mapping of the Al-Qaeda network.
Yeah.
Very good.
The other buzzword we're going to bring down high reliability organizations and design systems. So that's the military folks, they're a high reliability organization, and to achieve that, it has actually a very particular structure that sets sort of parameters of what you can do, and then the design systems which is like, I would like this too, so kind of like that. So those two other, I work in that space a lot, so those are sort of two other buzzwords that we want to go down that.
Please.
This is something I've been thinking about all week. So I look at human service provider networks and organizational networks and human services, and I'm kind of, maybe this is a question is it just can't be part of research, but if you map a network and you can very clearly identify what is missing, to increase the robustness of this tie is missing, or this is where the bottleneck is, and it's a very practical, in this city, in this network, this intervention would be huge. How do you deal with that without breaching confidentiality, in an ethical way? Have you made an intervention on a specific network you studied?
Tom might have an answer to this. My guess would be that if it's something like a service provider network, that there's nobody in that service provider network who would be unhappy that you helped them close a gap that's there. And so it's one thing to say what I'm going to do is help a city provide services for people that everyone in the city wants to do anyway, and they just can't see for their own constraints of their own resources and whatever. So would you breach confidentiality? Maybe. Would anybody care? Probably not. And so I think that would, it's going to be very case to case. But this is a problem that happens in many settings. That is literally the task of the consultant. You go into an organization, and that's exactly what they want you to do, is to find this problem, to solve that problem. So, Tom?
Just to add to that, my experience, just remember one thing in the project what we're trying to figure out is what physical spaces might be high risk for us for home partnerships with the There's a thing, granted data, from a few years ago that sometimes there's a lag between when you collect data and what you find. So sometimes the landscape that you eventually like find that, you know, pinpoint and stuff about, like it's changed, right? And so there might be some less risk with that. But as far as reporting, I would say, remember it's hard for one is like when we're discussing, if we were to find that certain type, like certain spaces, like if you're communicating that results academically, speak about it in as general terms as possible. Don't say it's like this place where that's the hot spot. Say it's like this kind of place, right? But because that specificity does matter as far as interventions, right? Like increasingly there are demands for when you're working with vulnerable populations, like community advisory boards, right? And there's a way that, you know, maybe your publication is speaking, you know, generally, but as far as like folks who really need to know it, like it's like, you know, perhaps you don't trust a government agency with some sort of sensitive information about where activities happening. But if you're talking about community advisory board, you can get that. You can relay the needs for information with them.
And it might also be, in many of these cases, it's kind of, we were asked a question in a recent review about, you know, what are we giving back to the communities we're collecting data from? And so one of the things we're giving back to the communities we're collecting data from is to help them see what couldn't otherwise be seen. And so I think in many times we're asking people to share information with us so that we can get a sense of the landscape. It's kind of our obligation to tell them what they're, you know, what it looks like. And you know, they may or may not be able to figure out what the pieces are, and if there's something that's embarrassing, we should do our best not to do that. But if it can help the people who are doing this work a little bit better, I think the more of that we can do, probably the better.
I think that that's become the standard in health research, is to be genuinely community engaged, and be partnering with your community, and giving them back the data from them, basically.
Yeah.
Otherwise, they don't know.
Right. Just a win-win.
Yeah.
Other questions, thoughts? What do you wish we'd done? Well, go ahead first.
And also, like, networks doesn't have to also be deficit-based. Networks are strength.
Yeah.
So if maybe like if you can uncover and you should uncover like features of the networks that are strength for that population.
That's a great point. Absolutely.
I actually have the same issue. We were talking about this last night, but because I work with scholars who do critical theory by using quantitative data, and I would say like they don't do social network analysis, which seems like a huge problem because a lot of our questions are network questions, right? But I wonder if there have been any conversations in your field about like how certain populations are being like discussed in the literature, right? Like low-income people of color, like how would kind of like describe their networks as giving them a lot of assets, especially when they haven't been able to get those things from formal institutions. Like how have you had conversations about like how their networks are depicted, you know, more straight?
Yeah, there is there are a growing. I think the history of this has been one of hand wringing and problem solving, and it's shifting towards like how do we solve the problem of deficits here, there, and there. Whereas I think it's shifting now to what are the disparities in these sets, and how do we balance them from one side to the next. I think there's been a language shift from deficits to disparities, and there's been a language shift from that's a problem to like how do we provide resources and capitalize on resources that are there. And so Michelle White, who's a pediatrician in our medical school here, has done great work in sort of in neighborhoods in Durham. And she has this great story, which I'm going to steal from her, which is she said she works on obesity and other sort of health, dietary health issues, and she put a map up at a community organization, and this woman in the back goes, "I'm effing tired of being mapped," right? And it's like, I don't want to see another map that shows where the high obesity rates are in Durham, right? Instead, they tell me what to do about it. And I think that kind of a shift is useful. And so from our standpoint, we want to know what the big picture is, 30,000 feet, get all the landscape elements. But the people who live there, like they know that people are unhealthy. They want to find a way to do something good with it. So I think it is useful to be sensitive to that. I'm not sure if you did, please.
I wonder if there's an opportunity there to like embed network findings then into like an evaluation methodology or framework where like you are evaluating both of those concurrent things and you weight them equally and like you are framing things of like what people are doing well and opportunities for growth. And so maybe that might be a space to like draw from traditional evaluation framework, and not as a way to discuss and interpret what you're finding.
Please.
Is there any language that kind of goes outside of the qualitative sphere within networks regarding positionality, or like what's kind of coming out of the constructivist grounded theory related to, say, for instance, you're creating your network not through panels but through interviews and reflexivity and all this stuff in social networks?
There's certainly discussions, people use the tradition in network analysis is to use ethnographic terminology for quantitative, to describe quantitative patterns and such. So we talk about roles and obligations and these types of things. But I don't know if there's so much coming out of, so is that the sort of thing you have in mind, or?
Well, like for instance, I'm interested in studying Arab immigrants, and so I will be conducting interviews, for instance, and obviously, well, I'm not Arab identifying, so the potential, especially those who will be communicating with me in English, is who they nominate, potentially is impacted by who I am as an interviewer.
Got it.
So I was just wondering if there's any language kind of, I mean, obviously like RDS could potentially help, or as we discussed, like targeted sampling and memory, but is there kind of more in terms of like?
Yeah, that's a great question. I don't have an answer for you. If some folks who have done sort of cross-linguistic data collection should chime in here, but my guess is that you're just going to that this is going to be a case where the initial testing and formative research, where you ask people and you say, all right, now that you told me this is what I'm taking from it, and do your best to work with a few close confidence that you can, before you actually go out and do the full field, to make sure that you're getting the answer out of it that they think you should be getting. And so that kind of back and forth is that's what we do in any standard survey, but it's kind of a good thing to know. Tom?
Following up on that, it's what I'm thinking is like less linguistic, but it's touching on something Ashton said, but right, also like as you're, I'm thinking about networks and data collection, but making sure that the categories, the things you're asking are like relevant to the population. Like I met somebody at Sunbelt last year who studies like informal peer networks in like indigenous communities, right? And one issue he ended up having was that the networks that he was collecting were so dense, because he would ask like, who are you like related to, or who's your cousin? And all the kids like viewed everybody as their cousins, so you had these networks that were so fully dense, you didn't really know how to analyze them, right? And so whether it's because of linguistic constraints, like how things are understood, or just like cultural, like having what relationships like in addition to sort of like how you present yourself and how you might be heard, but like also with your background knowledge, making sure that that your understanding of networks and relationships and like in those communities maps sufficiently onto their understanding, so that the questions you ask are meaningful, the data they provide your response are meaningful as well.
All right, please, last thread.
It's not a follow-up question. It's a completely separate question discussing interventions and network interventions. Has there been research on like averaging of time of when to have the second wave of panels to analyze? Say if it's only like just UN assembly, like 1 week or a 1 day program, of when the second wave should be hit on. Has networks had enough chance to change in that time?
Because especially like as a student, you're given a certain amount of time you can create. So a lot of these options of temporal components are kind of limited because you're not given 10 years.
Yeah, it's the beginning of the seminar Monday morning, and then it ends, Friday afternoon. And so you've got a week, and then you may do a 2 or 3 week or 1 month follow-up, and that's about it. Generally, the work we've been doing in the field has been that the interventions usually take 3 to 6 months, and so you typically have a baseline and then an immediate follow-up, and then either a 6-month or 1 year follow-up after that. Sure.
All right, folks, it's been a very long week. We have some people to really thank. Again, I just want to say thank you very much to the RAs. So in the back here, or somewhere. You've seen a lot of me this week, but I wouldn't be able to do any of this without having them in the back to do this. So it's a process that we just couldn't do, and they've done it for a few years now, and I think that they both love it, hate it, fear it, and dread it at the same time every year. And so there's a big sigh of relief that happens at Durham at about 2:30 on Friday of this week, and it's coming from this group, and so it really couldn't be done without them. We're really, really thankful to IID and to Kathy Peterson. What's that?
Yes, Stockholm syndrome.
I'm working on that. We did. I encourage Stockholm syndrome. Very strong thanks to to Kathy Peterson and IID. We are guests in their space, and they've been more than generous to us, and so we really appreciate their help. And to, I don't know if Bernie's here anymore, but again, if you haven't had a chance, our big thank you goes to NICHD. They fund this process. This is our second round of funding. We're going to we have a third round that's going to be coming here soon, and so we want to make sure that we're up and well to them. So if you haven't had a chance to do the evaluations, please go onto the Slack, find that link, do the evaluations so that we can have those to go. If you absolutely despised this workshop and thought it was a waste of your time and money, I apologize. Let us know. If you loved it, we're never opposed to hearing notes from people so that we can include those in our reports and show them to folks. So don't be shy letting us know how we did. So again, thank you all very much, and hopefully we'll see you all again soon.